Thanks. Hello, everyone. It's my great pleasure to be here to tell you about Gibbs sampling and error correction. So I know you are tired, so I will keep this very simple. So I just want to convey two messages. The first is that, Gibbs sampling as a topic in computer science, it actually provides new techniques. To understand physics. In particular, the pre-thermalization of self-correcting quantum memory. And conversely, actually quantum error correcting codes are also very nice toy models for studying the non-worst case mixing time. Of quantum Gibbs sampling. So we will see later what do we mean by non-worst case mixing time and why it's super interesting. So our model today will be super simple. We will consider CSS stabilizer code. Which is just a commuting local Hamiltonian with X and Z checks. And we will consider a quantum system described by this Hamiltonian, which undergoes thermal noise. And in particular, the Hamiltonian is also very simple. The energy of an eigenstate is simply the number of violated checks. So we will just count the number of violated checks, and that's the energy. Okay, so then this system will undergo thermal noise modeled by quantum Glauber dynamics. And this is also called quantum Gibbs sampler. And this is also very simple. We just repeat the following process. First, we choose a random qubit. And then we will decide whether to apply a random Pauli error on this qubit. So hypothetically, if we apply the Pauli error, that could change the energy of the state. So we will also measure the X and Z checks acting on the qubit, and we will calculate the energy difference if we hypothetically apply the Pauli error minus the original energy. And we simply flip a coin, and we will either accept this Pauli error or not with probability of this quantity, 1 over 1 plus e to the beta times delta E, where beta is the inverse temperature. So this is very, very intuitive, because this is just saying that we are trying to locally decrease the energy. And because this probability favors low energy configuration, and the lower the temperature is, the more greedy we are in terms of decreasing the energy. Okay, so this is a detailed balanced Markov chain. So actually, the definition of mixing time says that no matter where we start from, we start from an arbitrary initial state. It will inevitably converge to the global Gibbs state of the Hamiltonian. And the time that takes for this to happen is called the mixing time. So now you can see that mixing time is really a worst case statement. It says that no matter where you start from, you go to the Gibbs state in T-mix. Okay, so now let's think about what do we mean by a self-correcting quantum memory. A self-correcting quantum memory is a very interesting physical system, which says that you can have a quantum state that encodes some logical information. That remains stable in thermal noise for exponentially long time. But now if we look at this statement, and of course throughout this talk, I will always assume that the temperature we consider is the final temperature below the critical point of the quantum system. So it has the memory phase. But if we look at this statement, it's sort of very interesting from the perspective of Gibbs sampling, because we can ask the question, what is the memory state? From the Gibbs sampling perspective, apparently it's not the Gibbs state, right? Because the Gibbs state is a unique fixed point of the Markov chain. So it doesn't encode logical information. However, the memory state still achieves some kind of thermal stability as in the definition. So it should share some similarity with the Gibbs state. But now we can see that it's actually very intuitive. Because the Gibbs state e to the minus beta h, if we think about zero temperature limits, beta goes to infinity, then this is simply the maximally mixed ground state. So we can think about the Gibbs state as at finite temperature, it will be some kind of thermal perturbation. Of a maximally mixed ground state or a random ground state. But the memory state is exactly the same perturbation of a specific logical quantum state, psi bar. That is the ground state of our Hamiltonian. So instead of perturbing the random ground state, we perturb a specific ground state, and that's our memory state. Okay. Now this is so simple, right? But the memory statement is saying something very interesting. It's saying that, okay, so now we give this memory state a name. We call it rho beta with a superscript psi. And we call it the Gibbs state within a logical sector, because apparently it goes by definition. Now, if we think about memory, it actually says that the quantum Gibbs sampler acting on the memory state will be able to keep it approximately unchanged for exponential time. This is quantum memory. But now, going back to the original definition of quantum Gibbs sampling, this is precisely saying that the Markov chain is a slow mixing Markov chain, right? Because starting from this memory state, it will take a very long time before we eventually, inevitably converge to the Gibbs state. Okay, so naturally, memory is associated with slow mixing. But now, maybe there's, yeah, please. C is some kind of constant. Yeah, think of it as a constant smaller than 1.
Okay. So it depends on your system, or just some random
C is
thing?
a constant that depends on the Hamiltonian.
Okay, thanks.
Okay. So now the question is, okay, so T mix is exponentially big, it's big. So in some sense, this is saying that maybe the Gibbs state is hard to prepare, right? Just intuitively by definition. But now if you think about it, this is saying something troubling, because our memory state is also some kind of Gibbs state. So how do we prepare the memory state? Okay. And the answer is also very simple. Because we are trying to create the Gibbs state within a logical sector, we can think of the thermodynamics process as an encoding process. We just imagine starting from the perfect ground state and just run the quantum Gibbs sampler and hope that nature will naturally give us the corresponding memory states. Okay, so here is our hope. And we will draw this long arrow which indicates the time. Suppose starting from time 0, we start from the ground state, a specific logical state of our choice. And the hope is that after a short amount of time in the thermal noise environment, it will naturally give us the encoded memory state. And then, by definition of the memory state, it actually will stay stable for a long time. But in the meantime, due to the detailed balanced nature of Gibbs sampling, it inevitably will eventually converge to the Gibbs state, so the memory is lost. And, this is exponential. And this is also exponential, so there is some gap. But this intuitively could be very fast. It could be as fast as polylog n. Okay, so this is our intuition. So we are hoping that this is actually the case. And if we look at the literature of self-correcting quantum memory, the literature is proving this part. It says that if you start from the memory state at finite temperature, it stays stable. But it doesn't tell us about the first part. Okay, so maybe an interesting question is, can we resolve the first part to establish our intuition that, if we already start from the perfect ground state that encodes our logical qubit, it should quickly converge to the corresponding memory state in the thermal environment. And actually, it is also an interesting question from the perspective of phase of matter. So let's take there are many definitions, but let's take the simplest definition that two mixed states are in the same phase if there exists maybe a polylog depth sequence of channel that connects rho to sigma and vice versa, sigma to rho. So you have to prove both directions. So our physics intuition tells us that, if you claim to have a self-correcting quantum memory, then your logical state in the ground space should be in the same phase as the memory state at finite temperature, right? And if you look at this diagram, one of the two directions is easy. Going from the finite temperature memory state to the ground state is easy, because this is precisely what we mean by decoder in the error correcting code. And if we want low depths, we can demand to have a parallel decoder, which is often the case for these finite dimensional self-correcting quantum memories. But the top direction is an open question, which is resolved by my recent work. where we prove that there's rapid mixing within the logical sector. So starting from the ground state, you should be able to have a low-depth sequence of channels that gives you the corresponding memory states. So now it sort of resonates with what we said in the beginning, right? Because from the Gibbs sampling perspective, this is interesting because we are doing something fast within a slow mixing Markov chain. So this is saying that even if you have a slow mixing Markov chain, you can still converge quickly to the Gibbs state, or more precisely here we have the metastable memory state, as long as you can start from a good initial state. So intuitively this is clear, right? Because the ground state should be a good initial state for preparing the corresponding memory states. And that's what we are trying to make rigorous here. And I will tell you a little bit about the technical challenge. The technical challenge is that in physics, there is something, there's something called Mpemba effect. Mpemba effect says that hot water freezes faster than cold water. You know, this is a little bit counterintuitive, right? Because naively, if you put hot water into the fridge, it should become cold water first, then it will become ice. But actually, hot water will freeze faster than cold water. And technically, it's sort of hard for us to rigorously rule out that this doesn't happen in our CSS code system. And in particular, we are afraid of something of a shortcut, like going directly from here to here, without going through the intermediate stages. So whether we can rule this out is the technical challenge. And we are able to indeed rule this out, but proving this doesn't happen for the standard global dynamics is still an open question. What we do is to find a clever way to get around this. Using quasi-local dynamics. Quasi-local dynamics just means that instead of updating a single qubit at a time, we look at the box at a time. So the box will have side lengths roughly log n. And for example, let's consider the 4D toric code. The 4D toric code has energy excitations that are loops in 4 dimensions. So when we zoom into a box of qubits and we look at the energy excitations, it looks like loops. There are some loops within the system, and of course, there should also be some excitations that crosses the boundary of the box. And we sort of choose this clever dynamics by doing the following. We will look at this box, and actually we will freeze anything that intersects with the boundary. So we will not update the loops that crosses the boundary. And for the interior, we will actually resample. So it will be some different loops. And the resampling is according to the conditional Gibbs state, conditioned on the boundary configuration. And we can achieve this in polynomial time of the system size, which is log. So each update takes polylog n time. And we can also show that this box dynamics is rapid mixing via some kind of decay of correlation argument. So the number of boxes we need is also polylog n. So overall, this is sort of a polylog n time algorithm. Okay, so that's it. And for the next part, I will actually tell you something that is even more difficult and interesting. Okay, so the next question I'm going to ask is that, look, previously we are saying that if you start from the ground state, which is already a topological state, you can prepare the corresponding memory state in finite temperature quickly. But now I'm going to ask a further question. Can we create finite temperature topological order from a trivial initial state within thermal noise? This is asking, can we create our beautiful finite temperature topological order state for the Fourier Tori code starting from nothing? And you are not allowed to do anything fancy. You are not allowed to do like classical computing and so on. You only have thermal noise. And so in an upcoming work, we consider the following very simple idea. So let's still call it a conjecture. Conjecture 1, which I call self-correcting state preparation. And the idea is extremely simple. So let's start from the maximum mix state. And just do global dynamics at low temperature. And we claim that in polynomial time, it will give us the Gibbs state of the Fourier Tori code. Let me clarify that the polynomial time is actually cannot be made faster, unlike previously. Previously, we are saying that starting from the ground state, it converges to the memory state in polylog time. But this has to be polynomial because the left-hand side is trivial. The right-hand side is topological order. So you need polynomial time. And from the physics perspective, this is absolutely remarkable physics, right? Because this is saying that we just do quench dynamics. Because the maximum mix state can be understood as the infinite temperature state. And we just prepare the infinite temperature state and suddenly throw it into the low temperature bath. And we somehow believe that, topological order will naturally emerge in polynomial time. So how is this possible at all? And separately, from the Markov chain perspective, this is also saying something magical, because if you remember, previously we said that if you have arbitrary initial state on the left-hand side, if you have the Gibbs state on the right-hand side, it takes exponential mixing time. But here we are saying that as long as we have this random initial state, which is also trivial, it somehow can avoid exponentially slow mixing barrier. Okay, so next I will tell you a little bit about why this should be true or could be true. So to do that, let me mention a second conjecture, which is just the Ising quench. Ising quench is sort of saying that if we start from the infinite temperature state in the Ising model, in the 2D Ising model, which is just like a completely random spin configuration, and if we run global dynamics, it actually converges to the Gibbs state of the 2D Ising in polynomial time. Okay. Now there's nothing like topological order going on here, but this is still saying something very, very interesting, because the 2D Ising is also a slow mixing classical Markov chain. And we want to argue that conjecture 1 should be true. Essentially for the same reason. That conjecture 2 should be true. This is saying something very non-trivial because we are trying to create topological order while this is the classical. But maybe you can still see that they share some similarity. So if the Ising quench could work, maybe even the Fourier code quench could work. So I will skip this argument, and for my remaining time, I will try to tell you a little bit about why Ising quench is true.
Is this statement independent of the temperature of the global dynamics?
Low temperature. Any low temperature. Oh, because at high temperature, this is trivial because high temperature is fast mixing. Okay. So I will spend a couple minutes of my remaining time to tell you a little bit about why should you believe conjecture 2. Okay. So let's start with a special case. Let's actually not think about finite low temperature. Let's think about Ising quench at 0 temperature. You know, which physicists actually studied this a lot, and actually they call this enigmatic behavior. And you will see why. So 0 temperature dynamics is very simple. We just imagine we have a 2D system of spins, and every square is a spin, and every square has 4 neighbors, and you will just greedily flip to the majority of your neighbor. And if there's a tie, then you flip randomly. Okay, so here is what happens when you run this. Let's start from the infinite temperature Ising configuration, which is just completely random. And now we suddenly throw this into the 0 temperature bath. And, you know, maybe sometimes the good things can happen. Maybe sometimes it just magically cools down to the ground state, all plus configuration. And by symmetry, sometimes it cools down to the other ground state, all minus configuration. You know, life would be very easy if only these two things happen. But there is also a third possibility. And this happens at a relaxation time of L square. The third possibility is that you freeze into a stripe state. So you have plus here, minus here, and plus here. And once you go here, you can never get out. Because if you look at this picture, every spin is stable. Every spin majority is the same sign. Yeah.
You could have any number of stripes.
Yes. But yeah, that's also like that is also like stable. But in reality, maybe you only see one stripe. Okay. So now this seems bad news, right? Because how could we possibly cool down the system if it gets stuck? It turns out that at finite temperature, something else happens in addition to this. So at finite low temperature, you also see this kind of thing happening, but there's also something else happening. Because we are at finite temperature, these domain walls will not be completely stable. It will actually fluctuate left and right with speed roughly 1 over L. And now you can think of the vertical domain wall as doing some kind of random walk in the other direction. It's doing a left and right random walk on the 1D ring. And if you have two particles doing a random walk, they will meet with each other in polynomial time. So actually, you know, even if you land here, maybe you can still go back to either here or here with time L cube. So it will be slower, but nevertheless polynomial. And maybe this is the reason that you can create topological order in finite temperature. That's all. Thank you.
Questions? Please, if you have questions, please speak into the microphones on the two sides of the room.
Just a quick comment. I mean, it's kind of obvious from what you said. I mean, very nice results, by the way. But I guess sort of then for the Tori code is a bit of a sweet spot in dimensionality. Would you agree that sort of if we go to higher dimensions, it could be much harder to compare?
Oh, that's a good point. There is an example that even for 3D easing model, there are domain wall configurations that will completely freeze even at finite temperature. However, maybe here one can hope that the quench will not sort of magically land at these very hard domain walls. Maybe nature is sort of harder to conspire at higher dimensions. So even if there are bad configurations, maybe we can hope to get around that. Yeah, but here we're not. It's sort of different. Yeah.
Yeah, thanks for a very nice talk. I guess I think I'm asking a very similar question. I just want to clarify, like, which part of this is specific to or depends on topological order? Which part of it relies on the self-correcting property of the underlying code? Or like, is it possible to generalize? Is it possible to generalize this to things that are not self-correcting memory, or is like, I don't know if that?
Yeah, so I guess the reason that we're talking about all of this is just because we have a slow mixing Markov chain, right? So slow mixing Markov chain is what gives us self-correcting quantum memory, and maybe that coincides with finite temperature topological order. But if you don't have finite temperature topological order, then your overall is a fast mixing Markov chain, so everything will just mix to the Gibbs state, so there's nothing to explore.
And that's like is it a if and only if statement? Like, if it is not a self-correcting memory, then I don't have slow mixing. Gibbs.
Well, I mean, self-correcting memory implies slow mixing.
But it does the reverse hold, I guess, is the question. Or is that by definition, maybe?
Yeah, I guess the reverse is whether not self-correcting memory implies fast mixing.
Yes.
Yeah, I'm not sure there's a rigorous statement, but yeah, we're talking about, specific, for each specific model, we sort of know what's going on.
Okay, thanks.
Hi, thank you for this clear talk. Just as an experimentalist, I want to confirm I understand the motivation of the first part of your talk.
Yeah.
So you said for the first part of your talk, you want to achieve a target memory state, right?
Yeah.
But you're starting from a ground state?
Yeah.
Okay, then I kind of lost the motivation. I mean, a simple example, that's rhetorical code. Normally people will say the ground state is already a good state, but why you need to go to another state?
Oh, that's because, that's a very good question. Okay, so a concrete example is that if you have the ground state of the 2D Tori code, that's like very good, right? But actually it's not stable at finite temperature. If you turn on finite temperature, the state will quickly disappear.
I see.
So you have to have, if you want to have finite temperature stability, you have to be in some kind of thermal equilibrium, and you have to have slow mixing, so you have to have the blue part. Mm-hmm. Yeah, and then to create the state that is in the blue part, we start from the ground state.
I see. So should I interpret the temperature also kind of relevant to the error rate?
Oh yeah, you can just think of temperature as the error rate in the system.
So kind of I can maybe, is it correct to say with some, giving finite error rate on experimental real hardware, you want to kind of find a way to achieve the best memory state under that given error rate?
Yeah, notice that we are not doing quantum error correction here.
Yeah.
Here we are just saying that we prepare this state at finite temperature, and it will stabilize itself within the environment. You don't have to do anything to protect it, but if you have an experimental platform, for example, you can do error correction on the 2D Tori code. There's no problem with that.
Yeah.
But if you want to experimentally simulate, for example, 4D Tori code, then you just need to do some local quantum error correction instead of classical error correction to achieve that.
Okay, thank you.
I have a small clarifying question. So is the memory state uniquely defined, or does it depend on the dynamics you're doing?
Oh, actually, that's a good question. So the memory state definition depends on your definition of decoder, because eventually we want to be able to say that having the memory state, we can extract the logical state using a decoder. So your choice of the decoder will change the precise definition of the memory state, but the intuition is that the difference should not be significant.
So the choice of the decoder also changes the choice of the dynamics?
No, dynamics is just global dynamics.
Okay. Another question is the memory state the same state until exponential time? Like, it doesn't move at all?
Yeah, so it will not stay exactly the same. It will change very, very slowly. I guess you have sort of a decoding threshold. You want to be able to say that having this state, I can decode with probably 99%. So that will be the blue circle. And out of the blue circle, you will convert to the Gibbs state.
Okay, thank you.
Yeah, for the second part, are you able to create the Gibbs state or the memory state? I just got a bit confused.
Great question. So here, for the specific claim I'm writing here, it's just the Gibbs state because my initial state has no logical bias whatsoever. But if you start from the all zero product state, you will actually end up being the logical zero state. Because the initial state has a logical operator.
Thanks.
Sorry, you're saying that you want to rule out the shortcut from going from initial state to Gibbs state by this quasi-local dynamics. Could you explain again, like why this quasi-local dynamics can rule the shortcut out?
Great question. Yeah, I didn't explain this. So, yeah, like I said, so we want to be able to say that it's not possible to have this shortcut, and this is still an open question for the standard global dynamics. But our definition explicitly rules this out because we freeze the boundary. So we don't allow small loops to conspire and merge with each other. That's the bad thing that we don't know how to rule out with global dynamics.
Thank you.
So I have a question about the last sentence of your talk. What's the intuition of that L cube scaling?
First of all, the first part is that the domain wall moves at speed 1 over L. And that's because if you create like a small excitation on the domain wall, it could sort of potentially propagate without further increasing the energy. And maybe if you do some calculation, it's 1 over L. And then we understand this as 2 points moving randomly on a circle of length L, and they meet with each other in time L squared over the speed. So that's L cube.
But for example, the linear size of the system is of order L, why naively I should expect L squared, right? So for example, because the linear size of the system is L, and I just divide it by the speed, which is 1 over.
Oh yeah, yeah. I mean, this is a weird thing in random walks. So if you have 2 points doing random walks on a line, they meet in times L squared, not L.
I see. Should I expect, for example, that domain will like propagate diffusively?
Yeah.
Somehow?
Yeah.
I see. Thank you.
Hi, thank you for a really nice and really clear talk. I had 2 questions, time permitting. So the first was about the sampler that you used in your proof. So you say that it only takes polylog n time and it's quasi-local. So, but if it's not global dynamics, it presumably still gives us an efficient algorithm at the very least. Is that correct?
Yes.
So would you mind just explaining what your update rules are for this in the context of a general CSS code, maybe?
So this update rule works for maybe the general family of self-correcting quantum memories on finite dimensional lattices. For a self-correcting memory on a finite dimensional lattice, you often have the behavior that the syndrome patterns will form connected clusters. Here we have the special case of loops, but in general, they could be also some kind of other clusters. But no matter what happens, we just freeze any connected component that touches the boundary and resample the interior of the box, and that just works.
And the resampling on the interior is done presumably using global type dynamics, or?
We just imagine, okay, so technically we are just saying that you think of the resampling as like one step as a black box, then you only need polylog n layer of such boxes. But of course you can ask whether you can implement this box efficiently. And that is the case for the for rhetorical, but maybe not in general.
Amazing, thank you. Is there time for one more question? Yeah. Okay. And lastly, I had a question about how you, like what criteria implies slow mixing. So one thing that you said, of course, was if you have stable finite temperature topological order.
Yeah.
Is this equivalent to something like a confinement property around each of these ground states? Like having...
Great question. Yeah. So actually, let me emphasize this example. So there's a recent paper by Andy Lucas group, which says that if you look at infinite dimensional quantum systems like quantum expansion code, you have thermodynamic triviality. So the partition function is completely analytic, and yet you can still have slow mixing and quantum memory just because of confinement. So so I guess for these infinite dimensional systems, topological order is not necessary for quantum memory.
Thank you so much.
So you said that some of these properties hold at low temperature. So I wonder if that's T smaller than some critical temperature or just sufficiently low, and also if some of these time scales, like maybe do they diverge if you get closer to that temperature, for example?
I see, So I guess for these results, we can only prove sufficiently low finite temperature, but I guess you would expect it to be true for any temperature below the critical point. Sorry, was there a further question?
Yes.
All right. If we don't have more questions, let's thank the speaker again for a very clear talk.